Good morning, good afternoon, and good evening. Thank you very much for joining us for today's webinar on scalable high-fidelity trapped ion qubit state detection with the Hamamatsu Orca Quest IQ camera. I am very pleased to be welcoming Dr. Andrew Van Horn, who will be giving the presentation shortly. He should be joining us now. Hi there, Andrew. Hi there.
Hello.
Hi there. Before we start, I just want to run through a few house rules for everyone that is going to be joining us for today's webinar. First of all, it is being recorded. So if you have to step away from the presentation or there's something you miss during the actual presentation itself, don't worry, it will be available on the optics.org website in about 24 hours. And of course, if you do ask any questions during the presentation, we will try and get through as many of those at the end of the presentation in the Q&A. If for any reason we don't ask your question or try to answer it, don't worry. Someone from the Hamamatsu team will reach out to you directly to try and follow up with any queries or questions that you may have. What I'm going to do now, first of all, is, like I say, I'm very pleased to welcome Dr. Andrew Van Horn, who has very recently received his PhD in electrical computer engineering at Duke University. Working with Dr. Young-Sang Kim, his graduate research focused on scalable hardware solutions to enable trapped ion quantum computing. So a very big congratulations on very recently getting your PhD. Well done.
Thank you.
Mhm. Okay. What I'll do now is I'm going to turn off my camera mic. I will hand over to you, Andrew, and you can begin your webinar presentation. Thank you very much.
All right, go ahead and share. Thank you for the introduction, Robert, and thank you to Hamamatsu for sponsoring this webinar, SPIE for putting it on as well. Can everyone see my screen? Are we presenting now?
Yes, you're all good.
Okay, thank you very much. Yes, so as Scott said, in my PhD research, we're focusing on trapped ion quantum computing with a particular focus on how to enable greater manufacturing scalability, how to produce more units, and how to produce systems that have a larger overall qubit count. So in this webinar, we're going to be looking at three things primarily. First, we're going to explore the model of a detection fidelity for the ytterbium-171 qubit. In our lab, we primarily use ytterbium-171 ions to store and process our quantum information. So we'll go through the model, the theoretical model for how we determine the detection fidelity. We'll also characterize the performance of the Orca Quest Q-CMOS camera as it relates to our qubit state detection. And then we'll demonstrate this high fidelity qubit state detection in one of our trapped ion experiments. So real briefly, trapped ion quantum computing. There are many hardware platforms that we can use to realize quantum computing systems. We particularly like to focus on trapped ions for a number of reasons. One of the main ones being they have a very high fidelity gate operation. The 2-qubit gates are generally significantly better than many of the other hardware platforms out there. One of the main challenges for trapped ion quantum computing systems is the scalability. For a long chain system, we can really only trap about 20 or 30 qubits in a single chain. And there's a lot of work that needs to go into shuttling them around a trap if we want to reach hundreds to thousands of qubits. That's more on the qubit control side. What I'm focusing on is the detection side. So if we have 100 qubits, if we have 1,000 qubits, ions, how do we image them effectively? So a brief overview about how trapped ion quantum computing works. We use this device called a surface electrode trap to confine the ions to a linear space. The way this works is we have an oscillating RF field, which creates a one-dimensional pseudo-potential that traps the ions along a single axis. We can then use static DC electrodes to confine the electrons to, or the ions to within a particular region within this trap. So you can imagine this potential well, we could move it to the right, we could move it left, and these ions would be shuttled along this linear axis. So each ion allows us to gives us a single qubit that we can encode in the electronic states of the ions, in the energy levels of the ion. So this gives us a programmable spin state that we can use to store and process information. So if you're familiar with a qubit model system, each one of these ions can represent its own qubit. In order to perform single qubit gate operations, we shine a laser onto one of the ions, and that can cause it to flip between the 0 state or the 1 state or perform any single qubit rotation operation. What's unique about ions is because they're charged particles in the same potential well, these charged particles are going to repel against each other. So what that means is we generally cool these chains down to their ground state. So ideally, the motion is absolute at zero. But if there's any perturbation, any motional perturbation, we get these quantized motional modes within the system. So these are just vibrational modes that cause the chain to move in a particular way. And because this is so low energy, these vibrations are actually quantized. So we can define them as a bosonic type particle. In the literature, these are usually called phonon modes. So we can use this bosonic mode to enable long-range interactions in order to perform spin-spin operations, in order to perform two-qubit gate operations. The other interesting thing about these is we could use these bosons as an additional quantum resource. So instead of just focusing on individual qubits, if we can encode that information into the bosonic states as well, that gives us a much larger state space to store and process the quantum information. But for a two-qubit gate, we would generally shine two lasers onto the ions in order to perform a multi-qubit operation. So that's in the state preparation and control side of things. Now we'll move on to the rest of this talk about qubit state detection. So given that we have a qubit that's prepared in either the zero state or the one state, how do we extract that information from the system? We can shine lasers onto the qubits in order to control them, but we need to read that out in order to complete the overall operation. So in order to do that, let's take a look at the energy level diagram of this ion. So these circles here represent the ions that are trapped in a chain. And here we see the energy level diagram of one of those qubits. So in the ground state manifold, we can encode the qubit in this hyperfine structure. So a dark state, zero state will be in this f equals 0 hyperfine level, and the bright state will be in this f equals 1. This hyperfine structure is basically a joint coupling between the nuclear spin and the electron spin. So we're kind of moving the joint coupling between the two when we perform this perturbation. So the dark state can be prepared in this f equals 0 state. And then by applying a perturbation that's resonant with this 12.6 gigahertz line, we can excite that from the dark state up to the bright state. So turn the ion into a bright qubit. This is usually done using external microwave fields if we wanted to apply the gate to all ions in parallel, but it's also commonly performed using a two-photon Raman interaction with the relevant detuning. So we can prepare the qubit in this bright state, but now we need to read that information out. In order to do that, we can look at an additional level of the energy level diagram. So if we look at this P1/2 manifold, this is a dipole transition from the S1/2 manifold, we can perform what's called state-dependent fluorescence, which basically means we can excite this transition from the MF equals 0 to F equals 0 P1/2 state, and that's going to cause the ion to be excited into this upper manifold. And then when the energy decays back to the S1/2, we will emit a photon. So it's important to know that for physical reasons, this transition from the F equals 0 P1/2 manifold to the dark state is forbidden. So this creates a closed cycle fluorescence loop where we'll continually pump it up to this state. It'll decay back to this manifold, pump, decay, which will cause the ion to continue emitting photons. So if it's in the bright state, it'll emit a bunch of photons, but if it's in the dark state, it's not going to excite up and it won't emit the photons. So then the goal of state detection is we design a system to collect as many of those photons onto a sensor as we can. Here are some example imaging specifications. The scattering rate of these systems is usually around 10 million photons per second. So we're emitting quite a lot. But the detection efficiency, which is given the probability that given any photon is emitted from the ion, what's the probability that we are able to successfully detect it on the CMOS camera? That runs about 3.4%. Part of that is from the limited numerical aperture of the imaging system. So the ions are emitted kind of isotropically, or the photons are emitted isotropically about the ion. We can only collect about a 10% solid angle with a 0.6 numerical aperture. So we're getting 90% loss from there. And then there's also quantum efficiency loss in the imaging sensor itself. So all of these come together along with other insertion losses to give a detection efficiency. And from here, we can identify our overall detection rate. So how many photons per second, how many photoelectrons per second, rather, does the camera or does our imaging sensor actually detect? So at this point, I want to introduce how we actually discriminate between these two photons or these two states. So as I previously mentioned, the emitted photon or the detected photon rate is about 200,000 counts per second. This is about as bright as a star if you were to look up into the night sky. So in this model, I will say right now, this is a simplified model. We're going to go a little bit deeper as the presentation progresses. What we can do is what thresholded state detection, where we identify some threshold and say if we receive more photons than this threshold, it's in the bright state, and if we receive fewer, then it's in the dark state. So to think about this, we can look at the photon detection probability, which is basically the probability mass distribution of detecting a certain number of photoelectrons on the sensor. So the probability of collecting a certain number of photons. For this model, it's just a simple Poissonian distribution where the mean value is just the number of photons that you collect per second times the overall exposure or detection time. So for this system, we are scattering at some rate, or we're detecting at some rate. There might be some background dark current from the camera or just scattered background light from the rest of the system that we have to account for to get our mean value. If the ion was prepared in the dark state, then it would just be the background noise times that time. So then for thresholded discrimination, we identify it as bright if the number of photoelectrons received is greater than that threshold, dark if it's less. And that means the bright and dark error is effectively your false positive and false negative rate. We can define a total error as the average between the two. So using the typical performance values we described before with a threshold of just one photon, we can look at how this would evolve at different times. So here what we're looking at, each frame, I'm increasing the exposure time, the detection time, and we see this orange line is the bright count distribution. So given that the ion was prepared in the bright state, this is the expected photon number distribution that we would receive. And then the blue is the dark state. So the area under the curve here in green is a successful detection. The ion was prepared bright and we're measuring it as bright. But the area in red here would be a error. So it's prepared bright, but because those photons are to the left of the threshold line, we misidentify them. So that counts as an error. And with this model, we would be able to just increase the detection time arbitrarily high, set an arbitrarily high threshold, and we'd be able to have very high fidelity detection. But the problem is the model that I had just given you doesn't capture everything that's going on inside the ion. So in order to get a more accurate model, let's go back to our energy level diagram. So I previously stated that this decay from the F equals 0 P1 half manifold to the F equals 0 S1 half manifold to the dark state is forbidden. And while that's true, there are other mechanisms that can allow this bright state population to flip or decay into this dark state. So while we're driving this transition, because the detuning, the frequency offset between the F equals 0 and F1 half manifolds is so small, only about 2.1 gigahertz relative to the overall line width of the system, relative to 19.7 megahertz, which is the line width of this level, there's a slight probability that this bright state can be excited into this F equals 1 manifold. Because this is gigahertz relative to megahertz, the likelihood that this happens is given by the by this gamma, this line width, divided by the separation, the additional detuning needed squared, comes out to about 22 and 10 to the minus 6, which is a small probability. But remember, we're scattering at a rate of 10 million photons per second. So that means this actually happens fairly often. So this off-resonant scattering can cause the bright population to excite into this F equals 1 manifold, which can then decay into the dark state. So the ion is able to go from the bright to the dark state. Likewise, this transition from the F equals 0 to F equals 1 state, from the S to the P, is also possible. The frequency is a little bit higher. It requires more energy, a larger detuning. So the rate at which that happens is a bit lower, but still something we need to account for. And this would cause the dark state to, again, excite into this upper manifold and then decay into a bright state. So this causes a state flip rate, which is proportional to the applied intensity of the detection beam, applied intensity of this laser beam. Yeah, so we have a certain dark flip rate and a bright flip rate that happens as we are detecting our system, which isn't very advantageous because if you're trying to detect your ion, if you're trying to detect your qubit state, and it flips from one state to another mid-detection, then that can cause plenty of errors. So in order to incorporate these state flip rates into the overall model, the equation is a little bit complicated, but I'll try and unpack it here for you. So we can look at that same photoelectron probability mass distribution, and we see kind of a couple different regimes. So this first part of the equation basically represents the number of photoelectrons we would expect to get given that the state was that no state flip occurred. So given that throughout the entire detection process, the population stayed bright or it stayed dark. And then this red part here, slightly more complicated, is given by the number of photoelectrons we receive, assuming that one state flip occurred. So we prepared it at bright, we started emitting a bunch of photons, and then it flipped dark and stopped emitting, or vice versa. We started dark, we detected, and then it flipped bright midway through. There are some higher order terms that happen if there were two or three or four or n state flips that occurred, but because the state flip probability is so low, this probability is low enough that we can discard it from our model. So this model, you can see it has some Poissonian probability mass distribution, some CDFs, a lot of variables in here. Fortunately, we can just plug it into our simulation and get the result out. And given which state we prepare in, whether it's the bright state or the dark state, can plug in different values for these variables to get what our expected distribution looks like. So when I simulate this as before, so we're sweeping the detection time at different frames, we see this bright count distribution has this residual tail at the low photoelectron count number. This basically, the way to understand this is that this is the ion starts in the bright state and then quickly turns dark before we're able to detect enough photons to make a state detection. So it fits maybe one, or we detect maybe one or two photons, and then it flips dark, and then it just stops emitting photons. So with this residual tail, you can see we're no longer able to just arbitrarily push out our detection time or detection threshold because we would keep integrating this error to the left here. So this residual tail comes out to be at the ratio of this dark pumping rate to the photon detection rate. In this system with our photo detection rate as described here, this comes out to 4 times 10 to the minus 3. So then what we can do is we want to find the optimal parameters to get the minimum detection time. So we have two variables. We have the threshold that we can use, or the threshold at which we put the state detection, and we have the overall detection time. For an ideal sensor that doesn't have any readout noise, ideally you would just set this threshold to 1, and you would then minimize or find the minimum the time at which the detection error is minimized. So here we're seeing those detection error curves at different thresholds. You can see as we increase the threshold, we're unable to reach these lower detection error rates, and we can find the time that minimum curve. As you increase the exposure time, then the dark pumping or the bright pumping channel starts to come into play, and you see a reduction in your overall efficiency. So we can identify the optimal point. So with this ideal sensor, we can look at what detection fidelities we're able to achieve at different detection efficiencies and at different background noises. So I'm assuming the camera is perfect. The camera has no readout noise, and all of this is just coming in from the imaging system. So we have some background photons that are leaking in, and we have some loss from our detection system. So the way to look at this curve or this plot, this is a contour map where the blue lines represent contours for the minimum detection error, and the orange lines represent the time required to achieve that minimum detection error. So I primarily want to look at the blue lines here. A few things to note is background noise after about 10 counts per second, below 10 counts per second, anything lower, we start to see diminishing returns. So once you cross this 10 counts per second threshold, obviously reducing the background noise will improve the fidelity, but we start to see diminishing returns. Above that, that background noise does dominate. But the detection efficiency is always important. You can see here as we increase the detection efficiency, our fidelity gets lower in kind. So if we're able to reduce or improve our detection efficiency by a factor of 2, our our detection error will be reduced by a factor of 2. So having as high detection efficiency as possible always will help us. So this is with an ideal sensor. At this point, we can go and look at the physical device characteristics we're using. So for CMOS-based detection, the way a CMOS camera works is you have this photosensitive layer, which basically when a photon hits this photosensitive layer, it will create free electron hole pairs. These free charges can diffuse through the photosensitive layer until they hit this charge transport layer, at which point the electric field pulls them in towards the readout circuitry. The readout circuitry basically consists of a capacitor that collects these charges, and outputs then a voltage, and a transimpedance amplifier circuit that converts that charge into a stable voltage source that can be read out by an analog to digital converter. This produces an affine electrons to count mapping. So given some number of electrons, photoelectrons that are received by the circuit, we multiply that by some gain from the ADC and from the charge readout circuitry. And there's usually some dark offset from the analog to digital converter as well, or from the circuitry. So an affine mapping to convert the electrons received to the physical counts that are output by the ADC that we read out from the sensor. So the important parameter for state detection is readout noise. So if we, throughout this readout process, there's some probability of getting a slightly different count than the actual ones corresponding to the photoelectrons received, just due to readout noise from the electronic circuitry. So if I cover the sensor, if I have a fully dark environment, and I collect 100,000 samples, I can measure the histogram of the dark noise. So this is a roughly Gaussian noise distribution, kind of breaks down at these lower fidelity, or at these lower probabilities. Yeah, and you can see the camera counts go from 200 to 210. In this camera QCMOS camera that we're using, the gain, so the electrons to counts mapping, is about 10. So when you go 10 counts away from the next one, that's where you would expect the next photon. It's probably a bit easier to see it on this plot to the right. So here we see the dark count histogram that's similar to what we have on the left. So this is with a dark sensor. And in the orange lines, what I did was I exposed the camera just long enough to get an average photon count of 1. So I have a very dim light source, very short exposure time. And you can see the distribution here looks roughly Poissonian if it was on a log scale, but we have to convolve the collected photon distribution with this readout noise. So for each one of these readout noises, we convolve, or for each one of these photon counts in number of photoelectrons that we receive, we convolve that with the readout noise, and we see this blurring. If the readout noise were 0, we would expect to just see a bunch of delta functions sticking up through here, but the readout noise causes the count distribution to kind of blur together. So that's one of the main features of this camera, is that the readout noise is low enough that you can actually resolve these individual photon peaks. That's one of the main marketing reasons for the development of this camera. So with each of these peaks, if I receive photoelectron counts here, I can say with about 80% accuracy that I received 1 photoelectron in the exposure duration. There's obviously some probability that I actually received 2, but I had just low readout noise, which made it seem like I only detected 1, or vice versa for 0. But the ability to discriminate these camera counts is closely tied to this readout noise. So how does this affect our overall fidelity? So you can see here, when what I'm doing is I'm sweeping the readout noise across the different frames, and we're plotting the bright state and the dark state detection. When the readout noise is low, we can resolve those individual peaks. So each peak represents the instance of receiving one, two, three, four, a discrete number of photoelectrons. But as that readout noise increases, those peaks blur together to the point where we can't distinguish them. And what happens for our detection model is as we increase the readout noise, if we just kept this threshold here at one, we would start to get a lot of error from the dark state. So this forces us to push our discretion, our detection threshold further out, which, as we discussed before, integrates more error on the bright state. So here I'm calculating the optimal detection threshold at each of these time slices. And you see the readout noise below about zero point 0.2 or zero point 0.3 electrons RMS, we start to see diminishing returns, but above that, we see significant detection error increase. So 0.3 electrons RMS seems to be where we get diminishing returns, which is good to know for future camera development. So at this point, just to take a quick step back, this is the full detection fidelity calculation for the camera system that I just discussed. It contains a handful of physical constants, physical values that are intrinsic to the ytterbium-171 ion and the way that we're performing this detection. But we have a handful of these experiment values that we can tweak. So once we have a system in hand, we can change the magnetic field strength, the detection time, the discrimination threshold in order to optimize our overall fidelity. These green boxes represent imaging parameters. So when I'm designing the system, I can design a system that has a particular collection efficiency, quantum efficiency, choose a camera that has a certain readout noise in order to get the best detection error that we can. Our general requirements are shown here. So background count less than about 10 to 20 electrons per second is good enough. Obviously, lower is better. Same for the readout noise, 0.3 electrons RMS is our cutoff where we start to see diminishing returns. We generally get collection rates of around 150 photoelectrons per second. And we want to set our threshold as low as possible and have a short detection time to minimize those flip errors that happen in the middle. So comparing different detection methods, most systems in trapped ion quantum computing have used PMTs to perform state detection. The primary reason for this is because PMTs have a very low readout noise. So any detection fidelity paper that quotes a very low fidelity was probably just using PMTs because they have this detection error. Camera-based systems in the past have always had a higher readout noise, which has meant that any system that uses a camera is going to be sacrificing their detection fidelity. So these PMTs are great with that low readout noise, but the problem is they do have a high per unit cost, meaning as we scale to dozens to hundreds of qubits, we have to buy a separate PMT for each ion in the system. They also have a fairly large pixel size, which means the imaging system to project our ion chain onto these PMTs generally has to be large because you need a fairly large magnification. Another thing is these PMTs force a specific ion spacing, which is a bit of a nuanced argument here, but for the ion chain, we can control the spacing of these ion chains by adjusting the voltage solution, but when we do that, it adjusts that motional frequency spectrum, which is useful for the types of quantum simulation applications that we're interested in. But with PMTs, we're kind of locked into a particular ion arrangement because we only have one device per channel. Whereas for a camera system, one of the advantages is the higher spatial resolution allows us to control or adjust the positioning of the ions more dynamically and between experiments so that we can get different motional mode configurations that might be useful in our system. So historically, these cameras had a much more favorable scaling. So any system that needed hundreds of qubits would usually just go for a camera and sacrifice that fidelity. The smaller pixel size meant you can actually compact the imaging system significantly as well. However, the recent developments in camera-based imaging technology have created cameras that have a low enough readout noise that we can achieve comparable detection fidelities to the PMT systems while maintaining all of the advantages. These cameras are still fairly expensive, but the break-even point between the PMTs and the cameras comes out to be about 30. So if you have more than 30 ions, it makes more sense just to buy one expensive camera because you only need one device rather than buying 30, 40 PMTs. Um, yeah. So now we can look at how this camera actually, let's characterize this camera in our actual system. So for Qubit state detection, for these ion state detections, what we want to do is focus as many of the emitted photons from a single ion into a single pixel. The reason for that is if we were to bin to larger pixels, we would just increase the readout noise. So our signal to noise ratio, our contrast there would always go down. So the best option for us is to focus as many photons into a single pixel as we can. So I can look at the detection efficiency. I can calibrate that fairly easily by trapping a ytterbium-174 ion. This is an ion that doesn't have that hyperfine qubit structure that I described before, which means if I shine that 370 nanometer detection beam light onto it, it'll follow a simple two-level scattering model where I have gamma is a physical constant, ISAT is a physical constant. So if I sweep the intensity of the detection beam across a range of values, I can fit the resulting curve to the overall photo detection efficiency. So with this, we can see for a 1 by 1 pixel, we're able to achieve a photon detection efficiency of around 1.6%, which is about on par with what we expect from our PMT-based systems. But the camera that we're using, the QCMOS camera, should have a much higher quantum efficiency than the PMT systems. And we see that reflected when we increase the ROI. So if we increase the ROI to a 3 by 3 or a 5 by 5 area, we're able to achieve a detection efficiency that's close to what we theoretically calculate. So we expect a collection efficiency of around 3.4%. We're able to get up to about 3.2 when we expand the ROI. So what this tells me is that we are collecting all the photons we expect. We're just having trouble focusing all of them into a single pixel. This is for a couple reasons. One is just the aberrations are difficult to control when you're working with such a high numerical aperture and trying to focus to such a small spot size. So we had to spend a lot of time just optimizing the aberrations to get within the Airy disk. Another channel is the Airy radius is within a pixel, but some light, about 15 to 20% of that light, will spill into higher number Airy rings, which will spill into neighboring pixels. And also there's potentially some crosstalk between pixels. So if there's even just a few percentage crosstalk, then that's going to reduce our collection efficiency. One good thing while I'm talking about crosstalk, in our system, we are imaging the ions with the ions are spaced about 5 micrometers apart. We have a total magnification in our system of about 5x, which means each ion will sit about 5 pixels apart from each other on the camera sensor. And we see here, once we get out to that 5 pixel limit, the proportional intensity crosstalk goes down to about 10 to the -4. So we're seeing very low intensity crosstalk between ions, which is very good for state detection. If we're lower than this 10 to the -2, 10 to the -3 level, any photons which do leak out to that neighboring ion, they're going to be at such low probability that it does not contribute significantly to our total error model. So we're able to spatially resolve each ion fairly well, which is good for scaling the system. So I want to look at the how we characterize the readout noise of this camera. So I showed you a readout noise distribution for a single pixel. In our system, so the QCMOS camera has a 2000 by 4000 overall pixel area. We don't need that many pixels. We only need ideally 1 pixel per ion. So we create this 256 by 128 sub ROI just to reduce the overall transfer bandwidth from the camera. And we can look at the pixel readout noise across all of these different pixels in this sub ROI. And we see that there's not much spatial distribution. There's a few, lines here and there corresponding to pixels that share the same readout circuitry. Maybe there's a bit more noise on one circuit, but in general, it's kind of salt and pepper noise. We're not seeing any significant variation across the sensor. And most of the pixels, about 80% of the pixels, should be within that pixel readout noise spec that we needed. So less than zero point 0.3, we start to be good. We will have high detection fidelity. Um, yeah, so this is the readout noise. You can also look at the dark current of our camera. So by collecting multiple exposures or multiple frames at different exposure times and fitting to a linear model, we can look at the background noise. So here we do see a variation across the sensor. This, I believe, is primarily due to just leakage from our experiment. The dark current from the camera should be like less than 1 electron per second, photoelectron per second should be very low. So this is just background noise coming in just scattered from our experiment. But since it's low enough, since it's less than about 20, we didn't need to worry too much about optimizing it from there. Um, so we do see this variation, but it's within 15 to 20 photoelectrons per second. So that variation doesn't affect our overall fidelity too much. So using these parameters and using the fidelity model I described before, I can calculate our expected detection error across all of these pixels. We see kind of the same salt and pepper. There's not really a statistical variance across the sensor, it's just kind of random which fidelity we'll achieve. And we can see that about 80% of our pixels, we should be able to get a detection fidelity of around 3 or 4 times 10 to the minus 3. So this is just a cumulative distribution. The way to read it is, for this error, 4 times 10 to the minus 3, 90% of the pixels should be less than that. So now we have our theory for what we should expect from the system. We need to wire it into our experiment. So what we use is we use the Arctic control system. This is kind of the workhorse in the labs here at Duke. It contains a bunch of modular components that can connect to various devices in the lab. And they've developed one card called the grabber interface, which is able to interface with the camera link, which is a protocol that is available on the QuarkQuest IQ camera. If you're interested in any of the code, any software that I present here, I have some representative snippets for how I interfaced with this controller into the Hamamatsu camera that are available at this link. So this OrcaQuest camera outputs a high bandwidth camera link interface that we can read in through the grabber. This grabber card can then send that to the Arctic controller. And in order to close the loop, we need to synchronize the camera exposure to the rest of the experiment. So we want to make sure we're exposing at exactly the right time with real-time control over when that happens. So the Arctic controller sends out a TTL trigger. That TTL just triggers the camera to expose for a certain duration. And then all the other controls in the experiment go through this system. So we then use the USB interface of the OrcaQuest to update any other parameters in the system. So this would be to set the exposure time, set parameters like the sub ROI settings, things like that. But we can also use it to monitor the frames through non-real time channels. So this USB is going to be non-real time, but we still get all the frame data through it, so we can monitor it while the experiment is running. And then this PC communicates to the Arctic controller over networks to load and receive the data from the experiment. It's worth noting that the Arctic system in the gateware, in the software running on this controller, provides us with 16 programmable ROIs. And the way it works is we define 16 ROIs within each frame, and the Arctic gate will return the sum of the counts of each ROI individually. Instead of feeding the entire camera link data back to the host, it takes that data, it takes that frame, chunks it up into these ROIs, sums the values within the ROI, and then gives that value back to the host, just to reduce the processing bandwidth within the controller. So using the Arctic system, this effectively limits us to only being able to detect 16 ions at a time. This, I want to note, is a limitation of the gateware itself. So if we needed to expand this to a larger number of ROIs, we could do that. It just requires rewriting some of the gateware running on the Arctic controller. And for our experiments, I was actually able to achieve higher number of ROIs by reading in the frames through the USB interface, storing them locally on the computer, and then in post, after the experiment was completed, just aligning those frames to the specific experiments that were run on the Arctic controller, and then using post processing to identify the ROIs and do the same thing where we just extract the counts for those pixels of interest. So we can achieve higher numbers of ions with the Arctic system. You just have to go through the USB to do that, which means processing it in non-real time. But it's once the experiments run, processing the data after the fact is not too much of a challenge. That's not something that necessarily needs to be done in real time, unless you're doing like mid-circuit measurements. But then you have 16 ions that you can detect mid-circuit, and then the rest of your ions just detect with non-real time. So in order to identify the ROI, in order to identify the ion locations, we have an automatic ROI script that can run on the Casly, on the Arctic system. So the way this works is I identify a sequence of, I basically perform a rolling shutter where I program the system to read out just a one by one pixel, but I change the location of that pixel between frames. So at different frames, I collect the data from different pixels in order to reconstruct the full image. And from here, I can sum all those values across the horizontal axis in order to identify the vertical location of the ions where they're bright, just a simple peak search. And then I can take a profile across this value in order to identify individual peaks for each ion to identify the horizontal position. So this gives us the position of each ion within the system that we can use for the detection. So for a single ion, we are able to achieve a detection fidelity of 99.6% with a fairly low detection time of 50 microseconds. This detection result is on par with previous publications using the same detection scheme, the same ion, but with PMTs. So we've been able to demonstrate detection fidelities with a camera that are comparable on par with PMT-based systems, which is pretty good. Here we can see the actual experiment data from that run. This histogram is the actual number of photon counts or photoelectron counts that we received. The curves are fit to the theory model, and we see good agreement between our theoretical model and the data that we captured. So with optimal data collection, I think we could push this fidelity up to 99.8%. Like I said before, about half of our photons right now are spilling out into the neighboring pixels. So if we can optimize that and keep the same detection efficiency or keep the same quantum efficiency and all of that, we should be able to push this collection efficient or this detection fidelity even higher than the PMTs because the QCMOS camera has a higher quantum efficiency than the PMT-based systems. I also ran this system on a long chain. So here we have a chain of 20 ions, and I specifically designed this one to have an uneven spacing. So you can see the ions here are kind of bunched together. The ones further out are over here are further out. These dark spaces just represent dark ions that I placed within the chain. So the bright ions are what we can use to store and process quantum information. So these are our qubit ions. And then we just have some other ions that are spaced in here just to break up the chain a little bit. We're able to get an average detection fidelity of 99%. A little bit of variation between pixels or between qubits, just depending on if the ions were kind of bridged between two pixels or if they were concentrated on one pixel. So I have a few ideas for future directions for this work that I want to bring up before I close. So the first is heralded entanglement. So for trapped ion systems, sometimes one way that we are looking at networking multiple systems together is to use this heralded entanglement scheme, which looks like this, where basically we make both traps emit a single photon. We put them through some sort of beam splitter to combine those photons, and then we detect them on a photodetector. Currently, we're using PMTs for these photodetectors, but I could imagine with a large-scale system, if we're going to have 100 different chambers working in parallel, it would be very useful to be able to detect all of them with a single sensor. And the ability for the camera to detect, to distinguish between 0 photons received, 1 photon, and 2 photons would actually be very useful because if you receive 2 photons on a single detector, that tells you something differently than if you receive 1 photon on one detector and 1 photon on the other. So that photon number resolving would be very useful. Another possible direction would be pixel binning. I mentioned before that as we increase the area of the pixels, then it increases our readout noise. But the readout noise only needs to be around like 0.25, zero point 0.3 electrons RMS. So if we can make a camera that has even lower readout noise, then we could bin a larger region. So if I binned a 3 by 3 region, then I just need a readout noise that's 1/3 less in order to achieve the same readout, in order to receive the same readout noise spec. The readout noise just goes basically as the square root of the area of the pixels that you bin. So this would be a way to increase our total collection efficiency of the system. But that relies on camera hardware that can achieve lower readout noises. Another avenue would be for the camera development side is in-camera binarization. So currently we're sending the full frame of data to our main control system, but we're sending 256 by 128 pixel area, and we're really throwing out all but a few pixels because we only need the number of pixels corresponding to the number of ions that we're actually using, the number of qubits. So putting some sort of intermediary processor, whether that's on the camera or whether it's some other device, to take in this high bandwidth data stream and just detect on the ions that we care about and return some low bandwidth binary value that's just, is the ion bright or is it dark, would save a lot of processing power on our system. And then lastly, I this work was done using the ytterbium qubit, but there are other ions that we could use to perform trapped ion quantum computing, and each one has its own trade-offs and benefits and trade-offs. One that I want to note here for barium, a lot of systems are starting to work on barium, and with state detection in barium, we can achieve much lower dark and bright pumping rates, and with that, we should be able to achieve very low detection fidelities. So 3 × 10⁻⁶, so a 3 order of magnitude improvement over the ytterbium system. But the camera, because it has low readout noise, will allow us to be able to reach the fundamental limit. So we're limited no longer by the camera specs, but by the qubits, the ion species itself, and the physical atomic properties of the ion. So with all of that, I'd like to acknowledge my collaborators, Seiyun Bak, Jiyoung Yu, and Kavya Ranawat, who are my collaborators here at Duke. Also, thank you to Hamamatsu for helping us get set up with the QCMOS camera, answering all our questions, and just collaborating with us to build something that really works well for our system. The Quantum Systems Accelerator Program through the U.S. Department of Energy for funding. The manuscript for this work is in preparation. I'm hoping to have that up in the next couple months. But if anyone's interested in a further discussion, feel free to reach out. So with that, I think we can open it up to questions.
Hi, Andrew. Hopefully you can hear me okay. Can you hear me?
I can.
Perfect stuff.
Yes.
Good stuff. Good stuff. We have had quite a few questions coming in because it's been quite an in-depth presentation. So if it's okay with you, I'm going to jump straight in with some of the questions that we have had.
Yes.
Obviously, if there's anything that's not quite in line with your presentation or you're not quite comfortable, just let me know and we'll move on to the next one.
Okay.
So we've had a question here asking whether mid-circuit measurement has been performed using QCMOS and how long it takes to perform branching, threshold, single-shot measurement with CASLI? CASLI?
Yeah, the CASLI is the main hardware.
Okay.
Yep. So mid-circuit measurement and branching has not been demonstrated with the QCMOS in our lab. I can't speak for other systems that have used it. Because it's a newer camera, I would expect not. As far as branching, for that, we're primarily limited by the CASLI hardware. The QCMOS is able to return data within a couple milliseconds, and we're able to process that data fairly quickly. The grabber, unfortunately, one of the limitations of the gateware that's running on the CASLI is it takes about 150 milliseconds for the data to be available to the kernel. If you're not doing mid-circuit measurement, that's not really a problem. You just buffer between experiments and you read it back later. But obviously, mid-circuit measurement, 150 milliseconds is way too long. Your qubit's going to decohere. So in order to enable mid-circuit measurement, I think we need to develop a custom gateware to run on the grabber. I think it's basically a limitation of the RTIO engine that's running in the CASLI. The RTIO engine takes about 150 milliseconds from what I've measured, from when it receives the frame to when it's available to the rest of the system. So that's where in-camera binarization, having this image processor as an intermediary device so that it can just return an SPI line that can be quickly read, would be able to make that much faster. But the data bandwidth and the capture rate of the camera, we haven't really been limited by that.
Okay, thank you very much. So we've also got another question here. Um, so manufacturing scalability transformed genomics through semiconductor-based sequencing. Do you envision similar manufacturing breakthroughs in trapped ion systems, eventually enabling quantum-enhanced biosensing, protein design, or single molecular diagnostics?
Yep. I'll say first off, I'm not an expert on the bioengineering side of things, but I do know that yeah, physical chemistry simulation is one of the many applications for quantum computing that we're primarily looking at. One of the things that we like about trapped ion systems in particular is that we have this motional degree of freedom that we can use to simulate bosonic Hamiltonians, to potentially model vibrational states within a molecule, for example, or these dissipative vibrational states, things like that. Um, I think for a trapped ion system, if we can get 20 or 30 even controlled qubits, then that gives us, 30 electron sites. So think about that's at that point we're able to start breaking even on classical processing or even having some advantage over classical processing systems. Um, so yeah, for the long chain trapped ion architecture, I think we're close enough that we're within a few orders of magnitude that with current technology, if we can scale it down, if we can make the system more compact, higher fidelity, more stable, we could get to a slightly larger chain system and start doing some quantum advantage experiments. Now, scaling to the hundreds or thousands of qubits needed for larger ones, I think we'll definitely need some additional technological breakthroughs on the trapped ion, on the long chain trapped ion side. Other architectures have their own drawbacks and their own breakthroughs to make to achieve that as well.
Okay, thank you. Another one here is as trapped ion quantum computers focus on scaling and increasing fidelity, what do you think the future of qubit state detection will look like to enable a high fidelity and scalable trapped ion quantum computer?
Yeah. So for trapped ions, I do think cameras are the answer, just because we have uh, the QCMOS camera now has 9 megapixels. So if we can leverage all of those pixels for detection, then that we're basically unlimited in the number of qubits that we can detect with a camera. What does limit our detection is the field of view of the imaging optics. So right now, the 0.6 NA imaging lens that I have in the current system can only view about 100 ions in diameter before the edge ions start to come out of focus. So we could image an array, but arrays won't really work with the trapped ion architecture. Could be useful for like a neutral atom architecture where you have like a 2 by 2 array. You could potentially get hundreds or thousands detected on a single camera, which they usually do with the SCMOS cameras anyway. For trapped ion systems, I think meta lenses could be a good option in order to design a system that has a wider field of view, maybe multiple different field of views. That can image onto a single sensor. But meta lenses have their own drawbacks that would need to be addressed as well.
Okay. And for a researcher who is considering upgrading their current trapped ion setup from PMTs to cameras, what are some of the factors they may need to consider to have a successful transition?
Yeah. I think the main factor would be the ability to focus onto a single pixel. So PMTs generally are a lot larger. If you're using just a broad surface PMT, a wide PMT, then you have millimeters of clear aperture that you need to hit. That's very easy to achieve. Many other systems with PMTs usually use fiber coupled PMTs. So you would image into a fiber tip, couple that light into the fiber, and then direct that onto a PMT. So I think the main consideration would be just designing a low aberration imaging system that can collect as much of your light into a single pixel as possible.
Okay. Maybe just one or two, if you don't mind. What are some of the challenges you encountered while conducting this experiment, and how did you manage to overcome them?
Yeah, I like I said in the last question, the main challenge was just focusing all that light. I spent a couple weeks, a couple months just trying to optimize the imaging system. So I ended up developing a whole process to align each lens and characterize, do we have spherical aberration? Do we have coma? How much do I need to adjust each lens to minimize each of those aberrations in order to get the best collection efficiency as possible?
Okay. We have one here just congratulating you on your dissertation, enabling technologies for manufacturing scalability of trapped ion computers. Is the dissertation publicly available yet? I think you mentioned earlier that you're kind of going to have that information up together. And will they be deposited in Duke Space or any other repository?
The dissertation is not currently public because I still have about 30 days to make final manuscript edits before final submission. In 30 days, I don't know what Duke's how long they will take from when I hand it over to when it will be available. It will be available on Duke Space. Um, and there's potentially some embargoes that we might need to consider depending on the paper publication timeline and all of that. But I would expect to have it up on Duke Space at least within the year. But depending on the embargoes, it could be in within a couple months. But if anyone's interested in getting a preprint of the dissertation, I'd be happy to send that along to anyone who's interested. Just you can find me
Okay.
on LinkedIn or probably send yeah, I can send my email as well.
Perfect. Okay. With regards to hardware, is any special configuration required to have a USB for configuration setting and camera link interface active? If only uh, one be active at a time, is there latency for changing interface, or can both be active? And
Both can
is,
be
sorry, go on.
Yeah, both can be active at the same time. So we run camera link and USB in parallel all the time. There are specific drivers for the USB, but that's just provided by Hamamatsu, and we haven't needed any specialized hardware. I think it's a USB 3.1, so it didn't require a special card or anything.
Okay. And is the camera link more of a passive bus with raw data sent through with no handshake necessary, or should one consider it an active protocol?
You should consider it as a passive protocol. Camera link does like the protocol does support controlling parameters back to the camera and does support that handshake, but the grabber card that the Casly system uses, as well as the protocol defined in Hamamatsu's system, are only sending the data out. They don't have the ability to control parameters. There might be a handshake on the Hamamatsu side, but I know on on the grabber side, on the Arctic side, they only it's only a one directional input.
Okay, perfect. Thank you very much. Well, we are literally on the hour, so it's worked out very perfectly to kind of wrap things up there. Dr. Van Horn, I would like to thank you very much for your presentation today. Again, this is being recorded, so if anybody wants to catch up on going through the presentation again, if there are any slides you particularly wanted to see, I know that Andrew, you posted up a URL link to some additional information, so that will be in the slides as well. You can see the answer, the video on Optics.org in about 24 hours. And I hope, first of all, again, sorry, to thank you very much for your presentation. And I hope to see all of the attendees here at the next Optics.org presentation in the not too distant future. Thank you for attending. And finally, if you're enjoying the Soccer World Cup, I hope your team's doing very well. Thank you very much.